We have done the exact solution of spin systems using Bethe-Ansatz. Now, we will do the derivation of the van der Waals equation of state. This is called as a real gas, and we shall really stick to the gaseous phase of matter and not close to the transition. Okay. And we will talk about the critical isotherms, and we will also talk about the cluster expansion of the real gas. And in this connection, we will introduce the notations and the graphs. Basically, the expansion will be done in terms of diagrams or graphs, and these graphs will be calculated in order to calculate the partition function. So, let us start with this real gas, and we know that the Hamiltonian. So, this is real gas, or we call it as a van der Waals gas. Which means that the interaction effects are inbuilt into the system. So, H is equal to say for example, P I square over 2 m sum over I, you can put a m I as well, and then we have I and j, and say j is greater than I, and you have a potential which is u I j, and let us call this potential for the moment as some u, and we will have to now consider this effect of u, which has been left earlier, where we have talked about the classical ideal gas, which is without any interaction. So, we have to write down the partition function, the usual Gibbs correction factor, which comes because of Gibbs paradox, and then there is a 2 pi m divided by beta h square whole to the power 3 by 2. This is all known to you, and now this extra term that comes, which is beta u, and this of course depends on these coordinates r1, r2, rn. There are n particles, and then we have to do this coordinate integral. So, d cube r1, d cube r2. Let me not put the vector, but it means that it is a volume integral all the way up to d cube rn. So, this is the new term that we have to consider now, and this new term will give rise to this equation of state that we are very familiar with. It is p plus a over v square plus into v minus b equal to r t, instead of just p v equal to r t. So, we write down this. So, this will call it as a z u. It is coming purely because of the interaction term, and we have this u equal to u 1 2 and u 1 3, u 2 3, and all kinds of terms which are all pairwise terms, which are of the form which is written as sum over u I j, again j greater than I, and this is if you write it without this j greater than I, you simply have to say I not equal to j and introduce a factor of half to avoid double counting. These all well known, and this u I j is that depends on the u r I minus r j, and it is actually the magnitude of that, and so it is the potential between two molecules at a distance r I minus r j, and one can actually assume a form which is called as a Lennard-Jones form, for u I j, and this tells you that u of r is equal to some u 0, and so r 0 over r whole to the power 12 minus r 0 over r whole to the power 6, and is also called as a 612 potential because of this form, and this r is a variable and r 0 is some distance. So, u 0 denotes the depth of the potential, and R naught is the distance, or rather this R min, or this potential is minimum. So, this U of R is minimum at some R min, which is equal to 2 to the power 1 over 6 R 0, and so on. So, it has various, one can plot it and see the properties of this potential, and it is called as a Lennard-Jones potential, and it is usually the one that is considered there. So, this has a form which looks like, so this is a function of U as a function of R, and so this is 0, and so this becomes strongly, so this is R 0. So, that is a minimum. So, this is equal to minus U 0. So, is at a distance R 0, nearly R 0, I mean, so there is some R 0. So, this is minimum at this point, and so it is strongly repulsive at small distances and weakly attractive at large distances. That is a form of the potential, and so R less than R 0, we call it as that is the repulsion. So, that is repulsive, and as R becomes close to 0, it becomes strongly repulsive, and R greater than R 0, it is attractive. Okay. That is the form of the potential, but this form is difficult to deal with for real calculations, which we will also see later when we use the cluster expansion. So, instead there is a simpler potential is there, which has very similar properties, but definitely is easier to deal with mathematically, and that is U of R can be modeled as this is equal to infinity for R less than R 0. So, it is like a straight potential there, and it is equal to minus U 0, and we have R 0 by R, or I can write it as small r. So, this is if R is greater than R 0, and this is to the power s, and so this actually behaves like this. Okay. And so, this is again R 0, and this is that U of R, and s is equal to 6 is most common. So, let me just go back and reiterate what we have said is that we start with a pairwise potential, that is the molecules of the gas are interacting via pairwise potential interaction, and we have to calculate the partition function. The partition function contains now a new term which is ZU, and it has to be computed, and for that one makes a model for U to have this form, which is a Lennard-Jones potential. As I said, that it is a little more difficult to deal with, not that it cannot be done, but we resort to a simpler potential, which will eventually give us the equation of state that we are looking for, and which has a straight wall at R less than R 0, and it goes to infinity, and then it falls off as R 0 by R whole to the power s, and it is weakly sort of attractive at large distances. So, U of R, instead of this a form that is shown in the Lennard-Jones, it is modeled by just a sharp drop of the potential to from a positive to a negative value for R less than R 0. Okay. And as I said that S equal to 6 is most common. Now, we calculate ZU, and this is the important task that we have in hand. And once again, just to write this in terms of term that we have is So, it is exponential minus beta u and then all these volume integrals. Okay. So, that is what it is. Now, what we will do is that in order to calculate the ZU, what we do is that we introduce effective potential U effective. And what is U effective? U effective is effective potential felt by a molecule due to the rest. Okay. So, instead of dealing with U, we will deal with U effective, and then will of course establish a relationship between U effective and U. And so, this ZU becomes equal to ZU is equal to exponential minus beta U effective function of R and a d cube R, and this raised to the power n. Now, you see that it is like doing a mean field theory, where we have replaced the U by U effective, which is an effective potential that one particular molecule faces due to the presence of all other molecules, and that is why there are n of them. So, n independent molecules, we take the partition function, which is raised to the power n, because this is potential felt by just one molecule. So, this is partition function due to one molecule. Okay. Now, it is important to note that one, that there is a region of space let us call it as a V0, which is for each molecule which is excluded from the integral. So, one important thing is that when we write this whole integral, we consider these molecules as point particles, but there is a certain region that each molecule actually occupies, or there is a volume that each molecule occupies, which is say equal to V0. So, for each pair that we are considering, so for each pair one cannot occupy the space already occupied by others, by the other, let us write it this way. And there is also an important thing that in this region, which is this region of V minus V0, okay, the potential is smooth, that is the U effective is smooth, it does not vary abruptly in this region, which is the difference between the volumes V minus V0, which means that your U effective can actually be replaced by the average value of U effective. Okay. So, these are the automatic the implications coming out of this writing this the partition function in this particular fashion. Okay. All right. So, we will have to now compute ZU, which is nothing but equal to V minus V0 e to the power minus beta U effective whole to the power n. So, what we need to find is that V0 and U effective average have to be calculated self consistently. So, nothing much has been done excepting the fact that we have now introduced that there is a certain volume that each particle or each molecule occupies, and another molecule cannot come inside that region. So, there is a V minus V 0, and then we this was excluded in the integral that we had written earlier, and now we write this thing as taking out this factor which is V minus V 0, and you multiply it by the partition function that we have already written, and then raise it to the power n. And I hope that raising it to the power n is now clear, because this U effective is the potential that one molecule faces due to the presence of all other molecules. Okay. So, that is so the entire potential, pairwise potential, is replaced by this U effective average. Okay. So, the first thing, let us determine U effective average. Okay. So, let us find this out, and so basically what happens is that you can use this U effective n into that. This is equal to half into n minus 1 into U average. So, where is this coming from? This is basically the n by 2 pairs coming out. So, it is basically the number of pairs of the interacting molecules. So, n is the total number of particles or molecules, n multiplied by U effective average is equal to this is the number, and then each one of them is having an average potential which is U effective. Now, this distinguish between the capital U and the small u that we have written here, and this is of course a U average, and this can be written as or rather almost can be written as equal to half n square U average, and because we have just neglected this factor minus 1 or minus half from this because n is large. Okay. So, that gives an expression for U effective average, which is equal to half of n into U bar, and this is nothing but half into n, and we sort of make an integral from r 0 to some r star, and then we have a 4 pi r square dr divided by v and u of r. Okay. And what is this factor? This factor is really the probability of intermolecular distance to be between r and r plus dr. Okay. So, this is how the U effective can be calculated, and so U effective average is equal to half n by v, and then there is a 4 pi, and you have a r 0 to r star, and there is a r square u of r dr, and we will take this form that we have assumed here, and not the Lennard-Jones form, this form that you see here minus u 0 r 0 by r to the power s, and s we just leave it as floating, that is s is a variable, and as I said that s equal to 6 is most commonly used there. So, now this will give me a minus half n by v 4 pi and a u 0 and r 0 to r star, where r star is some value from it varies from r 0 to r star, and this is equal to r 0 over r whole to the power s and r square dr. Okay. In fact, because this is we can make it as capital R 0 here, just so let me just make it as a capital R 0, not changing much. This is just that because this limit is from R 0 to R star, just do not want to mix notations. So, this R 0 to R star. So, R 0 is basically the range below which the potential has an infinite discontinuity, repulsive discontinuity, that is it goes to plus infinity, and for r greater than that it goes to a small negative term at large R. So, this is the R capital R, and this integral is easy to solve, and so this u of r is taken as this is not r, this is s, okay, and r squared dr, and this of course gets you this n by v 4 pi u 0 r 0 to the power s and r to the power 3 minus s divided by 3 minus s, and it is taken from r 0 to r star, and so this can be simplified, and one gets it's half n over v 4 pi u 0 r 0 to the power s, and one has it as r star to the power 3 minus s divided by 3 minus s minus r 0 to the power 3 minus s divided by 3 minus s. So, that is the form for u effective, and finally, we can simplify this and write this as this is like half n over v 4 pi u naught, and we have 1 divided by s minus 3. We just change this minus, absorb this minus sign, and it becomes s minus 3, and you have r 0 to the power s, r star to the power 3 minus s, and minus r 0 cube. So, basically if you take this s to be greater than 3, which is what we have assumed right from the beginning, that s is equal to 6. So, if s is greater than 3 and we take this r star to be infinity, then this term drops out and one gets a simpler form for this. So, it is a minus n over v. Now, the minus sign returns back because you have a minus here, and this is equal to 2 pi over 3 r 0 cube and u naught, which is a range, and divided by 3 s minus 3 and so on, and this can be written as minus n by v a prime. So, that is the u effective, which comes as minus n by v a prime. And let me now go and calculate the other quantity, that is v 0. So, this is u effective is calculated, and now we go ahead and calculate v 0. So, this is number 2, which is basically nothing but let me use a color here. So, we have the two molecules are say touching each other, and so these are the two spheres that are touching each other, and we now take this as you know the centers of this and the center of this to be here, and now this is the radius, and we can construct a sphere of radius this, which is the distance between the centers of each of the molecules. And you have to pardon me for drawing a freehand drawing of a circle. So, this is equal to that. Okay. So, this is nothing but equal to this is 4/3 pi r 0 cube, and this is nothing but r 0, which is the radius or the distance, which is the basically the diameter of one molecule. Okay. So, what is this factor that we have gotten, which is n into n minus 1, that is number of pairs of the interacting molecules, and then you multiply it by 4/3 pi r naught cube, and if you multiply this becomes equal to 2/3 into n square pi r 0 cube, and this is nothing but equal to n into V 0. Okay. So, this is the volume occupied. No other molecule can get into inside this volume, because each molecule has a certain volume. So, that is given by this n into V 0, and that has to be excluded. So, one can calculate V 0 equal to n into 2 pi over 3 and r 0 whole cube, and this is equal to 4 n and a 4/3 pi r 0 by 2 whole cube, and this is called as the molecular volume. Of course, as you see that it is a half of the that distance which is shown here, and this is nothing but n b prime, where b prime is equal to 4 into the molecular volume that you see here. Okay. So, that is your b prime. So, now we can compute the equation of state. We now got both these quantities that were there and had to be computed, which is U effective and also the V 0, which was there in this form that you see here. So, if you call this as equation 1, then we now have both these quantities that you need. So, your U effective, this is equation 2, which is minus n by V into some A prime, where A prime is given by this quantity, this is equal to A prime, and also we have this V 0, which is given by this V 0 is given by this quantity, which is n b prime. So, let us call this as equation 3. So, we have a 2 and 3, with that we are going to put it in 1. All right. So, that gives us z equal to 1 by n factorial, and putting all the other old factors that we are familiar with, whole to the power 3 by 2, v minus v 0 and exponential minus beta u effective average, okay, and whole to the power n. So, this is the partition function now with all these interaction terms that are embedded into it. And how do we find pressure from here? Pressure is found from, so this, let us call this as equation number 4, and so pressure is obtained from the partition function by using 1 over beta del ln z del v, which is nothing but the del f del v with the minus sign, and this is equal to 1 over beta del v of this quantity, which is n ln v minus v 0 and minus n beta u effective average. Okay. So, they nicely factor out, and we get this thing as nkt. So, beta is 1 over kt, which is now this is v minus n b prime and minus n square over v square into a prime. So, that gives you p plus a prime, p plus a prime n square by v square. So, I take it on the other side, which is equal to nothing but n divided by v minus n b prime and k t. Okay. So, we can take it to the other side, this thing, and that gives us p plus a prime by into n square by v square into v minus n b prime is equal to n k t. Okay. Now, if you introduce reduced volume, that is volume per molecule, that is a small v, which is also called as a specific volume. So, this is equal to p plus a by v square and v minus b. This is equal to r t, where so your a is a prime n square and b is equal to b prime n a n and so on. And what you can do is that you can use this Avogadro number here and write this as the capital N can be written as small n into n Avogadro. So, these are the changes, and or rather the variables that are transformed, and now we get this equation which is called as the van der Waals equation of state. So, starting from the partition function for an interacting system or an interacting gas, pairwise interaction with really no form that is assumed, excepting that it is hardcore repulsive at small distances and weakly attractive at large distances, with a form which is given by this form that you see here, minus u 0 r 0 by r whole to the power s and so on. So, this is really that minus u 0 thing that you see here, this value and so on. Okay. So, for this really s has been kept as a variable till the very end, and it in fact turns out that it, as long as your s is greater than 3, this equation can easily be derived, the van der Waals equation of state. And let us do the critical points or the critical isotherms for this. And the critical isotherms can be derived as basically this critical point are predicted by this equation of state, and so they are at some Tc, Pc and Vc can be found by taking this del P, del V, this is at a given T, and Tc, Pc and Vc to be equal to 0. So, this and also the double derivative vanishes as well. So, del square P del V 2 again at a given T, and at Tc, Pc and Vc this is equal to 0 as well. And one can calculate these things and get this isotherms which are in the PV diagram. So, this is P and this is V. So, the T greater than Tc, we have this T, this is greater than Tc. Let me use a color for this. So, the critical one is like this, and So, this is for T equal to T c, let me write that here. So, T equal to T c, and we have this critical point here, and we also have for T less than T c, we have this as so this is T less than T c. Okay. So, you get this critical isotherm. So, they are at 3 different temperatures. The black one is for T greater than T c, and the red one is at T equal to T c, and you have also this term which is, so there is T less than T c. Okay. Let us now get into another topic, rather this is the solution of the partition function. So, here we have of course calculated the partition function for a given type of potential. Now, let us do a sort of cluster expansion, or which is also known as a high temperature expansion of these quantities, and we introduce graphs and different kind of notations in order to calculate these effect of the potential term by term, and by considering graphs which we are just going to introduce. So, this is another method of solution of or rather the leads to the solution of interacting systems. So, cluster expansion. Let us see what they are. So, once again we have a Hamiltonian which is equal to y equal to 1 to n, and p I square over 2 m I plus you have a u I j, and you can have j greater than I, or if you do not assume anything, then you put a factor of half, and let us just carry out without any half factor, but we know that in order to avoid double count we have to have this factor. Once again u I j is actually u r I minus r j as earlier. So, this we call it as u r I j. So, the canonical partition function is written as 1 by n factorial h to the power 3 n, and we have this volume integral and exponential minus beta h. Volume integral is nothing but the integral over the phase space over all those 3 n coordinates, and this. So, the momentum integral is easy to calculate because you can do that easily, because the interaction term does not involve any momentum. It only depends upon the positional coordinates or configurational coordinates, and the only place where momentum comes is in the kinetic energy. So, that is a Gaussian integral that one can do it. So, the momentum integral, this is just a revision of what we have learnt earlier. So, this momentum integral is 1 by h cube and d cube p. We are just doing it for one particle in 3 dimensions. So, it is minus beta p square by 2 m, and this is equal to 4 pi by h cube root over of pi by 2 m by beta whole to the power 3 by 2, and this is nothing but 1 by lambda de Broglie whole cube. Okay. That is the thermal de Broglie wavelength, and what we have used here is that we have an e to the power minus alpha x squared dx from minus infinity to plus infinity. We have it as root over pi by alpha, and because this integral is not from minus infinity to plus infinity, but from 0 to infinity, we bring in a factor of half, and this is all what has been done here. So, the lambda de Broglie wavelength, just to remind you that it has this form, it is 2 pi h cross square by m k t, or you can write it in terms of simply h, not h cross. Okay. So, so finally, the partition function that we have to calculate, the canonical partition function, it is n t and v. This is equal to 1 by n factorial and lambda to the power 3n, where all those h etc. are embedded in this lambda, and then you have a d cube 3n r. So, these 3n are positional coordinates and exponential of minus beta sum over these I and j, and you have a u I j, and presumably j is greater than I, then we do not need a factor of half. So, let us just write this as you can write it as z u, but let me write it as z n for a reason that you will see in just a moment, and we will call it as z n. It is t and v, and of course, it contains also the effect of the potential. So, this is z n t v, and once again we have to calculate this z n t v canonical partition function, which includes the effect of the interaction, the pairwise interaction between the molecules in a gas. Okay. So, for non-interacting systems, of course, you have the z n is equal to 1 because u is equal to 0, and otherwise you have these effects of the interaction actually enters through z n, which is what we have said. So, now consider or rather introduce f I j is equal to exponential minus beta u I j minus 1. Okay. So, this exponential minus, so that sort of lets us draw these. So, we have this Lennard-Jones, and so this is your u I j, which is what we have shown earlier. It is the Lennard-Jones form. We can also plot the other thing, which is so, and this one is like this. So, this red color is f I j and the black color is u I j. Okay. So, these things are plotted as a function of r. Okay. So, if you want to know that what is the relationship or rather how does it look like, so they have these are really aligned, that is the maximum of f I j and the minimum of u I j. Okay. So, f I j is non-zero for interacting system. But there is something interesting here, but this at high temperature f I j is quite small compared to unity. Okay. So, what I mean is that f I j at large temperature is a small quantity. So, this tells you that this f I j is an appropriate quantity that allows high temperature expansion. All right. So, we are going to calculate things in terms of f I j. So, just to reiterate that for the interacting system, this is equal to 0, that is the 0th order of f I j is equal to 0, and we can write down the partition function, which is we have already taken this n. So, we write it as V t That is I mean n is for the n particle sort of being there in the system, and we will soon call it as a n particle cluster. And because we have taken out this exponential, or rather replace the exponential by this Fij, it becomes a a product of 1 plus Fij. Okay. So, this is quite helpful in the sense that that we have now these products of Fij. So, there are terms which are Fij, Fjk, Fkl and so on and so forth, and you see that this Zn is what we have written, which is the configurational coordinates is integrated over an exponential minus beta u. Now, this beta u is written as 1 plus Fij, exponential minus beta u is Fij plus 1, and so this is simply product of Fij plus 1. Okay. So, that is the thing that we have to calculate. So, now we resort to what is called as a graphic expansion. So, we start drawing graphs in order to expand this product that you see here, and calculate these products using these graphs. And let us see that if you expand this Zn, I believe it is clear what is Zn and what is its relation to the canonical partition function that we want to calculate. That is here in this equation. Let us call this as equation 1. So, the total partition function, canonical partition function, is this factor, which is like this 1 by n factorial, the Gibbs correction factor, and the thermal de Broglie wavelength, which is lambda to the power 3n, and then multiplied by Zn, and this Zn is what we need to calculate, and as I said, that will do a graphic expansion of this. So, this is equal to d to the power 3n r, and it is like sum over Fij. We ignore these indices because they are these indices will all be there. So, Ij, and then there are terms such as Fij, Fkl and so on. Okay. So, all these terms will be there. There will be Fij, Fkl and Mn and so on and so forth. So, there will be 3 such terms and 4 such terms. Terms means this containing these F's. So, they will all be there. So, now pairing of indices will include all possible pairings. It will probably be helpful if we give an example in order to elucidate some of this. Let us talk about 8 particle graph. Which means that we talk about Z8. Okay. And so, these are written as they are numbers and circles. So, these are this particle number and they are written within circles. So, it is 1, 2, 3, 4, 5, 6 and 7, 8. Okay. And all possible pairings are possible in the sense that there could be clusters of 1 particle, clusters of 2 particles, cluster of 3 particles and 4 and 5 and so on, and arbitrary number of particles. So, we can take, so first example is that let us take terms of the form Fij, Fkl, okay, and in particular choose I equal to 3, j equal to 4, k equal to 6, l equal to 8. Okay. And so, for all these I, j, k, l, once again we write this 1, 2, 3, 4, a bit of exercise, but they worth it because then you understand what kind of pairing we are talking about, and let me show it with color. So, we have now 3-4 pairing, okay, and we have a pairing between 6 and 8. So, that is what is committed here, because you have I equal to 3, j equal to 4 and k equal to 6 and L equal to 8. So, these are the pairing. So, the corresponding expression can be written as this expression, that is this thing can be written as d cube r 1, d cube r 2, all these are integrated over d cube of r 5, d cube of r 7, and now we have this, let us introduce a bracket, and in which we have a d cube r 3, d cube r 4, and we have a f 3 4. Now, this are not independent integrals anymore, because there is a f 3 4 which connects the coordinates 3 and 4, and also these 6 and 8 are connected as well. So, this is d cube 6 sorry r 8 f of 6 8. Okay. These are the terms that we have for this, and if you want, they are symbolically can also be shown as this is like a dot with 2, dot with a 5, dot with a 7, and then we have a dot which is a 3 and a 5. There is a connection, we will just write it in a moment, and then there is a 6, sorry 3 and 4, not 5. So, 3 and 4 and 6 and 8, there is a connection, and now we can write this connections here as with the red line and so on. Okay. So, this term is factorized as above. So, this means that there are clusters of 4 one particle cluster, so 4 one particle cluster, 2 two particle clusters. That is considered for this z equal to 8. Let us see some other combinations. Let us call this as B. So, now let us consider a product of 3 Fij's. Okay. And in particular, let us talk about a product, for example, F12, F14, F67. Okay. And this can be written as, let me write down the expression and then we will show it in a graph. So, this is, so which are the independent or one particle clusters? 3 and 5. So, we have a d cube r 3 and we have a d cube r 5 and of course, r 8 as well. So, d cube r 8, and now we have these d cube r 1, d cube r 2, and we have f12. This cannot be factorized unless you do the integral, and of course, there are you have to also do, because 1 is there with 4 as well. So, d cube r 4, and we have f12, f14, and we have a 2 particle cluster which is f d cube r 6, d cube r 7, and f of 6, 7 and so on. Okay. So, so there are 3 one particle clusters, then there are 1 3 particle cluster rather, and one 2 particle cluster. Okay. And if you symbolically want to show it the way we have done it earlier, so we have 3 here dotted with a 5 here, dotted with 8 here, and then we have so we have this 1 which is connected to both 2 and 4. Okay. We will write that connection, and we also have 6 connected to 7. Okay. So, let me write down those connections. So, there is a connection here, there is a connection here, and then there is a connection here. So, this 3 particle graph can be written as for example, this one is the 3 particle graph. Okay. 3 particle graph. So, all possible combinations are there. So, there could be just a 1 particle cluster, 2 particles, 3 particles, 4 particles, 5, 6, 7, all they can be all connected to some of them or all of them. Okay. So, for example, I mean now it is important to show that, or rather it is important to keep in mind that graphs of a same topology, or which is also called as a connectivity. Let us use this word connectivity more sort of, which is more relevant in this, but different particle labels. Are distinct. Okay. What I mean is the following, this let me underline this, and it is also this one is underlined. So, what is meant by that is the following, that if you have a 1 and a 2 and a 3 and we have a 5 and a 6 and a 7, say for example, or 8, does not matter. I mean, so this one, these connections that you have, these are 3 particle graphs, but they are distinct. So, these are distinct, and because they are distinct, they have to be counted separately. Before you get lost with all these graphs and all that, let me just remind you that we are just simply trying to calculate the partition function of a interacting system or an interacting gas. And this is quite important to say that we are really in the gaseous phase and not close to the transition that we have talked about, this critical isotherms TC, PC and VC. So, we are really in the well behaved gaseous phase, because otherwise these expansions may fail miserably. And in doing so, we are writing down terms which are, so your this partition function has a form which is exponential minus beta uij. We change this label to Fij, and then it becomes a product. Now, when it becomes a product in terms of Fij, we have terms which are F12, F23, etc. All of them are there. They all would come pairwise, because it is a pairwise interaction. And also we have now considered for a given value of n, which is n equal to 8 is considered. We have seen that there could be possibility of some 1 particle cluster, some 2 particle cluster, some 3 particle, some 4 particle, 5, 6 and even 7, 8 particle clusters. So, in general, so the partition function for the interacting system can be written as So, this Z n V t is equal to sum of distinct n particle graphs. This is an important thing, and what we mean by n particle graphs. So, by definition, this n particle graphs are defined as n distinct circles. I mean, circles is what we are denoting it by, numbered 1, 2 all the way up to n with lines with basically red lines that we are showing, with red lines linking some or all of them. That is the definition of n particle clusters. Okay. And Zn is sort of, you have to sum over all the clusters, all possible clusters, and while doing so you have to keep in mind that this kind of a 2 particle or rather a 3 particle cluster has to be, all of these have to be counted separately. They are distinct and they have to be counted separately. Okay. So, let us just talk about an L cluster graph. So, an L cluster graph or this comprising of L sites is a connected L particle graph for which the integral cannot be factorized. That is clear, because if you consider L particle graph, then there is no way that the integral cannot be factorized. That you see that here in this there is a 2 particle graph which we cannot or rather there is a this connection of 3 cluster, and then this cannot be factorized any further. Okay. So, we give another example, say let us consider a 5 particle cluster and let us write them as 1 and 3 and 2 and 4 and a 5 here, and why it is a 5 particle is that there is a connection here, 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 there is a connection here. There is no connection between 4 and 5, and this can be written as in terms of expressions. This is d cube r 1, d cube r 2, d cube r 3, d cube r 4 and d cube r 5, and we have terms such as f 1 2, f 1 3, f 1 4, f 1 5 and f 3 4. Okay. And this cannot be factorized. We just introduce one more for today and then continue with the next class. So, let us talk about this identical and non-identical clusters. Okay. And what are identical clusters? There is 1, 2 and 3. This is equivalent to, we'll write those red lines, 1, 2 and 3, that's equivalent to 1, 2 and 3, and not equivalent to 1, 2 and 3. Please wait till I draw those red lines. Okay. So, this is connected and that is perfectly fine. So, 1, 2 and 3 that is connected, that is fine, and 1, 2 and 3 that is fine. They are all identical, but when all of them are connected, then that is not the equivalent. So, this is a difference between identical and non-identical clusters. So, even if they are identical clusters, there would be a degeneracy, and this degeneracy has to be taken into account. And when we consider the cluster integrals, these will become very important for us to consider. So, we stop here with this discussion for now, because this has to go on for some time, and finally summing over all these graphs or integrating over all these expressions that you see, and one can actually land up with the this partition function, which is what is our ultimate goal. So, we stop here for today and then continue in the next class. Thank you.